Good afternoon. I am just delighted and extremely happy to be here. It's been a wonderful, and many thanks for having me here today. There is no way in the world I'm going to live up to the expectations that he set up in the introduction, but I'll try to do my best. I think we really live in a very exciting world in the area of data analysis these days. As time has progressed over the last few decades, the number of data we can collect is just increasing exponentially. There is more and more and more data, not only images and videos, but also in bioinformatics and signal processing in general. And it's gotten to a point that it used to be the case that we had lots of models and not good ways of validating them. Now it's the other way around. We have way more data than we can possibly analyze. And so a few examples. Think of images. So the first image was taken in 1827 in France. And do you know how many images have been stored up to today? 3.5 trillion. And the scary thing is that nearly 20% was just the last year. It's believed that by the end of this year, 90% of the traffic in the internet will be videos. 90% of the traffic in the internet will be videos. So the amount of visual data is just huge. And for many, 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 many years in signal processing, we wrote all of our beautiful papers, and we tested them in one image, which is the image of Lena. But now this presents many, many challenges. So think about the computer vision problem. You're given an image, such as the one that I have here, and you want to put labels on it. You want to say that there is a person, there is a bike, there is a background, and so on and so forth. So one possibility is to just give one label, and that might be the standard classification problem. Then you have many more labels, but you don't know where the people are, so you want to detect them. Or more generally, you want to actually label every single tiny pixel in the image. So think about the number of possible labels you have. If you have 10 to the 6 pixels and you have only 10 possible object categories, right? It's already 10 to the 10 to the something, the number of possible labels, the kind of things you need to estimate in order to just come up with an interpretation of the image. And think now that there are not only 10 categories in the world, they are probably on the order of 30,000. So if you just take the exponent of number of categories to number of pixels, and if then you multiply it by time in videos, it's just humongous. So developing efficient inference and analysis and clustering techniques for these very high dimensional data sets with mixed categorical and continuous variables is becoming very, very important, and we are currently developing many techniques to do that. The same thing is true of videos. So here I'm illustrating two different problems. The first one I'll talk about a little bit, which is you have videos that have several moving objects, and what you want to do is to just segment the data into multiple categories. And this shows sort of the progress of the last decade.
That was the introduction.
That's one more source of data, audio. It's really good. Here, we have very more complex videos. So imagine now that you have very deforming and complex things such as fire, water, smoke, and you want to recognize them. And imagine that you had many categories of that kind. So how do you combine, in this case, perhaps dynamical models that describe how things move in a very non-rigid way? What about now having networks of cameras where it's not just one image or one video, but you have many of them and they are related, and you can no longer do things in a single computer, and you need to develop distributed algorithms that are able to integrate semantic as well as dynamic information from multiple scenes. How do you develop techniques that are able to integrate? And that requires distributed optimization combined with traditional computer vision. The same thing is true in the medical domain. How many of you have ever had a surgery? Done. You are all very young. This will increase as I proceed. Out of those who have had a surgery, how many of you asked or how skillful the doctor was before having the surgery? There was one smart person in the audience now. So as it turns out, there are believe it or not, about 50,000 people die in the US every year due to errors during surgeries. And it costs the US economy $2.5 billion due to the extra time people need to be in the hospitals and so on and so forth. So there is a very critical need of training the surgical residents better. So how can you possibly do that? The very first time a doctor does surgery on you is really the very first time, because they cannot practice on people, right? So how do you train them better? So what we are trying to do here is, can you just take data that you can collect with a robot? In fact, many surgeries today are done with a robot that is called the Da Vinci robot. And now you have temporal trajectories of the motion of a surgeon as a function of time. Can you use those trajectories together with the videos that you can collect out of a surgery in order to determine how skillful a surgeon is? And that builds on a lot of classical techniques from the electrical engineering community. I'm sure you're familiar with speech techniques that divide sentences into words and words into phonemes, and hidden Markov models that can be used to model that time series. The idea here is to discover what the language of surgery is. So what are the basic phonemes in the case of surgical motions? What are the basic words in the case of surgical motions? And naturally, what you can do is take a 2-hour surgery, divide it into tasks. Tasks can be divided into basic gestures, like grab the needle, insert the needle, and so on and so forth. So how do you discover that semantic information, and how do you discover skill out of motion data as well as videos? So that's another task. And the last one that I'm not going to talk much about today, but I'm really fascinated, is the fact that now we can get lots and lots of images of the brain. I guess we all know that the future of medicine is going to be personalized medicine, where ideally we could have the medical records of everybody in the world, and a patient arrives and we can just search for the symptoms that this specific patient has. What are other examples in the entire database of the world that have been similar? What treatments were given to that patient, and so on and so forth. We're definitely not there yet, and currently the databases in the case of medical images are much more reduced. But you want to extract a lot of semantic information about images. You want to extract what the different biological structures in the brain are, what are the fibers, what regions are connected to what. Do these connections change when you have a neurological disease, and so on and so forth. So we're developing techniques, and many here work in that area as well, which is extracting semantic information out of brain images. So what allows us to be able to develop techniques for these very high dimensional and very complex data? So we exploit, and in fact many in the community exploit, the fact that when you have data that comes from many possible classes, the fact of the matter is that the dimensionality of the data, even though it's very high, number of pixels for example, the intrinsic dimensionality is very low. So here I'm illustrating the case with faces. If I take pictures of you and you don't move, and all I do is to change the lighting conditions, the images might be very high dimensional, but the intrinsic dimension is, depending on the model, is either just 3 dimensions or maybe 9 dimensions. And therefore you can describe all the images of a face with, say, a 9-dimensional subspace of the space of all pixels. Therefore, if you have a database with humans, many humans, then you'll have 1 subspace per human. So in other words, each one of the categories we want to discover is a linear subspace. The same thing is true when you start looking at patches of images, and different regions in this case will have a different texture. So the zebra will have one texture pattern, maybe the water will have another, and so on and so forth. So if you look at the multiple categories that might be present in an image, the patches can be assumed to live in different subspaces. The same thing is true of several videos, or videos when you have several moving objects. If you just look at the 2D trajectories of these objects as they move as a function of time, you can show that under some conditions, this is a 4-dimensional subspace. So one moving object is a 4-dimensional subspace of whatever, how long your trajectories are. So therefore, this problem of segmenting videos with several moving objects is clustering data that lives in many 4-dimensional subspaces. You can do that for very complex videos now. Suppose you had a video that had fire on top of water, and what you want to do is to find the boundary. So as it turns out, you can describe the temporal local variations of the intensities as a function of time, again with a low rank subspace, and use that information to be able to decide whether you are in a region that is fire or water. And you can do the same thing now with videos. So you can consider every frame of a video as a data point, and you can consider the video shots of a movie as a low rank structure. So typically, rank 1 would be an absolutely static and fixed image, and as the rank increases, you're allowing a little bit more variability. So therefore, the problem of segmenting, say, a video that has Hillary Clinton and Obama in an interview, as you switch from shot to shot, the segmentation could also be done by approximating the data with multiple subspaces. So today I'm going to be talking mostly about precisely that task, which is given a data set, be it of faces, be it of videos, how do you cluster it into multiple groups where each group corresponds to a different low-dimensional subspace? So I'll first spend a few minutes describing you a little bit what the problem is more formally. I'll then talk about one methodology that I developed many years ago to do that interestingly takes techniques from algebraic geometry and combines them with signal processing type of techniques for doing the segmentation. I'll then talk about what's been the revolution of signal processing in the last few years, which is using techniques from sparsity to reconstruct signals. And I'll show how these techniques from sparsity can be extended to solve actually clustering problems, where you have many, many, many subspaces rather than just one linear equation. I don't think I'll have time, but you can also do this with low-rank techniques that I'll probably have to skip. And then I'll show you how these can be applied to two of the tasks that I talked so far. One of them is going to be segmentation of videos, and the other one is going to be phase clustering. All right, so the introduction to subspace clustering is as follows. If you only had a single subspace, then principal component analysis, which has been developed for many years now, would be one way of doing it. You have a cloud of points, you pass a subspace through it, and we all know since 2 centuries ago that that can be done using the singular value decomposition. Moreover, we know that the rank of the data gives you the dimension of the subspace, and this has been really the workhorse of machine learning, dimensionality reduction, signal processing. Many, many, many problems can be analyzed in this way. So what I'm going to be talking about today is an extension of PCA, where the data now lives in many subspaces. So a priori, I might not know how many subspaces there are, although in many of the applications I'll assume it's known. A priori, I don't know what the dimensions of the subspaces might be, and more importantly, they could be of different dimensions. And I don't know a basis for every subspace, and I don't know which point belongs to which data point, to which subspace. So the task is just given the cloud of points, give me a basis for every group, give me the segmentation, tell me what the dimensions are, and so on and so forth. So naturally, this is sort of a chicken and egg problem, because if I knew the segmentation, if I knew which point belongs to which subspace, this would just be, well, just do PCA for every group. I know how to do that. It's been known. It's been what business as usual. Conversely, if I knew a basis for every subspace, right, I just assign the data point to the closest one, right? The issue, and why this is a chicken and egg problem, is that I don't know the segmentation, and I don't know the basis. So the most traditional way is to actually iterate. Given the segmentation, find the basis. Given the basis, find the segmentation. But there are a lot of confounding additional issues that you want to handle. The data is never going to be perfect. It's going to be corrupted either by noise. It's going to be corrupted by missing entries. Suppose that it was face recognition. Suppose that I put glasses versus not. Suppose that I wear a scarf versus not wearing a scarf. Then pieces of the image are going to be occluded. And so there are going to be some entries that are corrupted either by outliers or missing entries as well. Suppose that I'm tracking an object. All of a sudden, it can become occluded. So there will be a piece of the trajectory that I actually could never measure. So that's what the challenge is that you need to deal with. So I'm not going to have time to review the literature, but there's been a lot of work on this area for the last 10 years. And the traditional way to proceed was this idea of iteration. Given the basis, find the segmentation, given the segmentation, recompute the basis. So why that was not necessarily a great idea? One, this is a non-convex optimization problem. It's very easy to converge to local minima. So what my initial segmentation is, when I start the process, is really critical. So if I start close to the minimum, then it works, otherwise it doesn't. The second issue is that a priori, I need to decide how many subspaces there are and what their dimensions are. And since in principle, I have no basis to assume that this is going to be of dimension 3 and this other one is going to be of dimension 4, the natural and easiest thing to do is to say, well, they all have the same dimension and that's one more parameter to be tuned. That can be done in a probabilistic way and so on and so forth. But the origin of the first thing that I'm going to talk about today was, is there a way that I could initialize these iterative techniques better? Is there a way that I could maybe come up with a purely algebraic solution to the problem? And how could I do that? And I'm going to tell you how we did that in a minute. But the winners, really, over the last 5 years have been method based on a technique from machine learning called spectral clustering that I'm going to describe in a minute how it operates. And therefore, I'm going to focus more today on this second type of techniques, and that's where the sparsity and low rank story is going to come in. And if you're interested, there is a tutorial that I wrote recently in the Signal Processing magazine that will describe many of these techniques that I don't have time to review in detail today. OK, so let me start with the first technique. So, is there any possible way in the world I could do clustering in closed form in an algebraic way? And even is there any way I could even get what the number of groups is using pure techniques, purely algebraic techniques? How could we possibly do that? So this is the way we did it nearly 10 years ago. So we said, all right, suppose that I just had a plane for the sake of simplicity. And I'm going to describe the plane with a normal vector. So we all know that. That's super easy. OK, so one plane, super easy to do. What about two planes? So if I have two planes, either the data point x belongs to the first plane that has normal b1, or it belongs to the second plane that has normal b2. And this or equation in the middle is the source of the chicken and egg dilemma. Because given a point x, I do not know whether it belongs to the first group or whether it belongs to the second group. So our key question was, if we are to solve this problem in closed form in any way, I need to get rid of this or. And so the main question was, how can we possibly get rid of this alternating minimization thing? And so the key observation was that if you take the product of the two equations, the product is 0, no matter whether you're in the first group or whether you're in the second group. And it's both ways, right? If the product is 0, then one of the factors must be 0, and so you must be in one of the groups. All right? So that's an equation now that doesn't have an or, that is not chicken and egg anymore. It's an equation that is global, and it represents both subspaces at the same time. So more generally, I illustrated this for planes in R3, but the general statement is that in general, n subspaces can be represented with polynomials. See, this is a polynomial of degree 2 here in X. So in general, they can be represented with polynomials of degree n. All right? And here's the key insight. Suppose that I had the polynomial. How would you do segmentation? Well, you look at the polynomial and you say, well, it has two factors. Each one of them is linear. And each one has the normal vectors that I need. So at a high level, the statement and the solution of the problem is absolutely trivial. Feed a polynomial to the data, factorize it, and you're done. So if this was one-dimensional data, you go back to Calculus 101, right? And all what you're doing really is, suppose that I give you two cluster centers. You're just going to fit a polynomial, in this case a parabola that passes through the two roots, and the roots represent your cluster centers. All right? So the main question is, well, how do you do the two steps? How do you fit the polynomials, and how do you factorize them? So the fitting of the polynomials is easy, because I can always just expand all the possible products that I could possibly get. And you're obviously going to get a basis. So in this particular case, if I have 2, then I'll get x1 squared, x1, x2, x1, x3. There are 6 possible monomials in 3 variables that I'm going to get. And the polynomial is always going to be linear in those coefficients. So at the end of the day, I can write everything in a compact fashion. I have a vector of coefficients of the polynomial and a vector of monomials of a fixed degree. In this particular case, I call it n. So for 2 groups, n would be equal to 2. So I convert the polynomial into just a linear equation on the coefficients. So if I'm now given many, many examples, right, for each data point, I compute all of the possible monomials that I can generate, and the null space of the embedded data matrix will give me the polynomial that I'm looking for. So this is really, I mean, I've done it here a lot more complicated, but this is really go back to Calculus 101, and you're just fitting polynomials in one variable. The only difference here is that I'm fitting polynomials in several variables. Okay? Is that clear to everybody? All right. So this was a very interesting thing. You could actually tell the number of groups. In everything I told you so far, you give me the number of groups n, and I compute, based on the number of groups that you give me, what is the degree of the polynomials that I need to put. All right? So what if you don't know? As it turns out, you can determine algebraically what is the number of groups by just searching for the degree such that the embedded data matrix drops rank. Okay, so there is a lot of algebraic complication. Let me make it the simplest possible way. Suppose, this was a one-dimensional thing. Suppose you had to just fit a polynomial to 3 possible roots, and you didn't know that you had 3 roots. So you say, can I do this with a degree 1? And you're going to say, well, there's no way I can pass a line through 3 different roots, so that's definitely not possible. Can I do this with degree 2? No, I cannot fit a parabola that has 3 roots. Can I do it with degree 3? Then yes, you can fit a polynomial at degree 3. So in fact, the very first time you can fit a polynomial is when you have the right degree. Otherwise, the solution, so in other words, this matrix will be full rank when you choose a degree that is less than the true one. If you now do it for degree 4, which is more than 3, then how many polynomials can you fit? Then you can do more than 1. It doesn't matter, but it is more than 1. So this matrix will draw rank by more than 1. So the next part is, okay, good. You have a way of fitting the polynomials. You have a way of getting the number of groups. The rest of it is to do the factorization. So we did come up with a way to do the factorization that was nice and reducible to linear algebra stuff. But in general, it's not great to factorize polynomials. If you just go to MATLAB, and if you compute the roots of a polynomial, if you perturb the coefficients, in some cases you'll figure out that your solutions can be way off. So it's the same idea here. If you're trying to factorize polynomials, when they are corrupted with noise, you can get bad solutions. So a big discovery was that you did not need to do that, and that instead you could just take the derivatives of the polynomial. And so the key theorem was that the derivative of the polynomial at a data point gives you the normal vector that you were looking for. And as simple as that. Why is that true? It's in fact Calculus 101. How many of you took calculus? Everybody, right? Okay, so if you have a surface and you take the derivative of the surface at a point, what do you get? If I give you this point, what do you get when you take the derivative of the surface? You get a normal to the surface, right? Right? We all know that, Calculus 101. So that's the same thing. It's like I give you a cloud of point, you fit a polynomial to them, compute the derivative. That gives you a normal to the surface. This surface that I have here is very peculiar. It's a union of planes. So the derivative at a point needs to be perpendicular to the plane. So I can get the normals just from the derivatives. Right? Anyhow, let me show you an application of this. So this is a movie from the 1920s. You're going to see here this guy comes in, and he's trying to plot a robbery with this other guy behind. And so now there is this beautiful lady that comes in. They're introduced. And now it's flirting time. So you start distracting the girl. You take the tiara out, you give it to the guy, and now that the robbery is done, oh, I'm late, so it's time to go. And she's very happy, but then she realizes the robbery, and poor her. All right. So as you can see, this is a video. This is actually a real movie. The movies were not very long, 100 years ago. So can I separate this video into several shots that actually correspond to the different events that are occurring? Of course, this is very, very complex. And the idea of fitting this data with multiple subspaces is an oversimplification of the problem. So I don't claim to be very semantic. But this is what happens if I take this polynomial method that I just described and apply it to the video. I need to reduce the dimensionality. So let's say that I take my I don't know, 100 by 100 pixels, and I reduce it to 5 dimensions, and I apply the method. And I'm going to do it in a moving window now in an adaptive. You've probably taken maybe adaptive signal processing, so there are these methods. So I can adapt the coefficients of the polynomial as a function of time. So what I'm showing here, this is one of the coefficients of the polynomial here. So this is time, and the y-axis is the value of one of the coefficients. Actually, this is the estimate of one of the normal vectors. So you see that it's not perfect at all. Like if this was perfect, I would say I will have one value, then I switch to another event, I have another value, so it will be piecewise constant. This isn't quite exactly the case, but you can see the introduction, I have a black movie just with the title, is relatively constant. Then the video starts and I have a huge peak, but then the empty living room. Then it goes down, and you can see that it's not perfect. There are a few oscillations here and there, but by and large, such a simple method, such as fitting a polynomial of degree 2 to the data, and taking the derivatives was able to discover the fact that there are different events in different parts of the video. Right? All right. OK, so this was, you know, a very nice, clean method, closed form up to degree 4. All I do is fit a polynomial and then factorize it or take derivatives instead. What is wrong with it? So there are two fundamental things that are wrong. One is that the data can be very corrupted, and it's very easy, as I said earlier, to get your polynomial completely wrong when the data is corrupted. Two, something that I didn't tell you is that the number of coefficients can grow exponentially. Think about all possible multiplications that you can have. As soon as you have lots of variables and the degree is high, you can have way too many to fit. So how could we make this better? And how could we deal with outliers? And how could we have a computationally more efficient technique? So this is what we did next. So we rely on spectral clustering. How many of you know what spectral clustering is? OK, a small percentage. OK, so let me take a little bit of time explaining it. So high level, this is all I'm going to do. Build a graph. Every data point is going to be a node in the graph. And I'm going to connect pairs of points by how similar they are. Okay. And as it turns out, and I'm not going to go into the details, if you compute this matrix of weights or affinities of how related every pair of points are, if you compute the eigenvectors of a matrix that is built from this similarity, for those of you who know, is the eigenvectors of the graph Laplacian, you can get the clustering out of the eigenvectors. Okay? And so that's what you do. You build the similarity, you get a low-dimensional embedding, and then you cluster. So the key thing for this method to work is that you build a good similarity. What is a good similarity? You would like pairs of points to have a similarity of 1 if they're in the same group, and 0 if they're in different groups. OK, so let's try to do that for data. Well, if I just had 2 clusters here, the distance between the data points will be a very good similarity. These 2 points here are very close. So e to the minus the distance will be nearly 1. These 2 points are very far. The distance is large. E to the minus the distance will be nearly 0. So that would be a great similarity to have. OK, let's try to do this for subspaces. So let's take this point here, and let's take that point there. They are very far, but they're in the same group. So e to the minus the distance is not going to be a very good thing. Let's take now 2 points near the intersection of the subspaces. They are very close, and e to the minus the distance is going to be high. So there is no way I can possibly build a similarity just by looking at the subspace structure. Moreover, there is no way in the world I can tell whether 2 points are in the same subspace just by looking at pairs of points. So 2 points are always in a line, right? Yes? So what is the minimum number of points that I need to put to figure out if they are collinear? How many? 3, right? So 3 points, I can figure out are in the same line or not. Yeah. So the same thing is true for subspaces. I cannot do it from 2 points. I need d plus 1 points if d is the dimension of the subspace to figure out are they in the same group or not. So in principle, you're like, OK, you cannot do spectral clustering anymore, so what do? So this last paper said, well, just take all subsets of d plus 1 points, figure out if they are collinear, coplanar, or whatever the generalization is, and just do it. And in fact, that can be done. But this is very combinatorial, because I give you n points. You need to choose all choices of d plus 1 points and do a calculation. It's no longer a matrix. It's not just ij. You need to build a tensor. There are way too many entries to compute. It's combinatorially hard. These other people, actually Jan Polyface is at ETH, not too far from here. What they did was to say, well, I don't care about the combinatorics. Why don't I just look at a point? I look at the k nearest neighbors, right? They will very likely be in the same group. I can just compute a subspace locally from the point in the k nearest neighbors. And then I'll just use the angles between the normal vectors. That's a very good similarity. All the points that are in the same subspace will have probably the same normal. And all the points in a different subspace will have the same normal. So the angle between the two normals will be a very good way to do it. Except, of course, that near the intersection, my local subspaces are going to be very bad, because the k nearest neighbors are going to be in multiple groups. So it's like, well, why don't we just go ahead and do that? So let me show you 2 reasons why real data might be problematic. The y-axis here is, well, the x-axis is how far apart 2 subspaces are. What are the angles between the subspaces? So obviously, the clustering problem is going to be easy if the subspaces are very far, and it's going to be very hard as you get closer and closer and closer. So so the y-axis is, if I take 2 subspaces at a time, what is the angle between them? What is the percentage of subspaces whose angle is less than so many degrees? So the blue curve is a curve of 155 videos, and it says, Jesus, moving objects do not move too differently from each other. The angle between them for the 155 sequences is between 0 and 5 degrees. So subspaces in real data sets can be very close. For faces, the other case is a case of faces. The angles are between 10 and 20 degrees. Right. So subspaces in real data can be very close. What about the nearest neighbor story? So the y-axis here is how many, if I look at a point, I compute the k nearest neighbors, how many are in the wrong group? What is the percentage? So for 10 nearest neighbors, you know, it's about 5% for videos of moving objects. But for faces, look, if I take 10 nearest neighbors, nearly 70% of your 10 nearest neighbors are in the wrong group. If you think about the last 10 years of manifold learning and dimensionality reduction, almost every single method relies on k nearest neighbors. So if you're trying to discover multi-group structure, the k nearest neighbors is not always the right thing to do. So what you really like to do is to figure out who are your neighbors without using just Euclidean distances. So how can you do both? How can I get rid of this combinatorial problem of searching over all possible pairs of neighbors without doing k nearest neighbors? So as it turns out, sparsity is the way to go. So all the advances on compressed sensing can be used for doing this. So what is it that we do? Okay. All we're going to do is the simplest possible thing in the world, which is I am a data point, y sub I. I'm going to express myself as a linear combination of all the other data points, right? I can actually always do that. You know, if you take the green point in R2, it's a linear combination of the 100 other points, right? And so that's all I do. So y is a linear combination of all the others with coefficient Cij. In matrix form, all it says is the data is equal to itself times a matrix of coefficients. I can always do that. It's always possible. In fact, C equals to the identity is a very good solution to that system of linear equations. But that would probably not be very good for what you want to do, because C equals to the identity, what does it say? I am a data point. I am equal to 1 times myself. that's not very good to discovering who my neighbors are, right? I'm going to be very selfish. So we are going to prevent you from being selfish. So we're going to say you write yourself as a linear combination of the other data points. So we exclude yourself so that the identity is not a possible solution of this. So what we say now is, suppose that because there are many solutions still, because this green point can pick any 2 points and it will work in general, in a generic setting. So what if you ask for a sparse solution? What is the sparsest possible you can possibly do? So if you write that far right green point as a linear combination of everybody, what is the sparsest you can possibly do? Because that green guy is a scalar multiple of any other green guy, you just need one non-zero coefficient. The green point is equal to a scalar multiple of some other green point, just one. So the sparsest you can possibly do is 1. Jesus, it turns out that 1 is the dimension of the line. All right? And moreover, the non-zero coefficients will always come from the same group you're in. Right? So in fact, let's just do that. You write every point as a linear combination of the other. The number of non-zero coefficients is going to be the dimension of the subspace you belong to. And the non-zero coefficients are going to be neighbors in the subspace-like way. And so I can pick one point that is very far apart, in fact. And I can resolve the issue of the intersections and the issue of distances that I had before. Everybody agrees? Anyone disagrees? No? So I just lied to you completely, because you can pick here this green guy, and it's possible that it will be a linear combination of that red and that blue, right? The sparsity level in this case will be 2, the same way that the green will write as a linear combination of any 2 points in the plane, so the same level. But the points are coming from different groups, so this is no longer true. So the theoretical question was really, well, when is this true? When is it the case that a sparse solution is subspace sparse? So when is it the case that if I search for the sparse solution, the non-zero coefficients will come from points in the same group that I'm in? So when will I get good neighbors? All right? The second part is I am a very lazy person, and I do not want to do L0 minimization, which is counting the number of non-zero coefficients. I would like to do something simpler, which is L1. And so because I'm going to be lazy, I want to actually ask the question for the lazy algorithm. If I do L1, when is it the case that the non-zero coefficients come from the right group? All right? So here is one answer, a sufficient condition. So the sufficient condition is the following. If the subspaces are independent, what does it mean to be independent? It means that the dimension of the sum is equal to the sum of the dimensions. All right, so 2 lines in the plane is very good because we've learned for a long time that 1 plus 1 is equal to 2, right? But 3 lines in the plane is not good because 1 plus 1 plus 1 is 3, which is bigger than 2. So it's a little bit of a strong condition, if you wish. But that's what I mean. So if this is the case, and if you have sufficiently many data points per class, then the L1 and the L0 as well will give you the right structure. So you can do construct a perfect similarity matrix when the subspaces are independent. All right? Is that clear?
That doesn't mean that the subspaces are different, then you would recover L0, it's just one sparse solution. Because then to solve L1, it doesn't give you like one sparse. It might give you like some sparse, but it's not the sparsity level 1.
What the theorem says is that it will give you a solution such that the number of non-zero coefficients will be equal to 1, or D, where the dimension of the subspace is D, even with L1.
Even that the subspaces are disjoint?
Not disjoint, independent, which is stronger than disjoint. Right? All right, so we were happy that we had a first theorem. And we went to look for applications in video. And so as I said, as I'm going to show later, we had independent subspaces in video. What does it mean to be independent in video? It means that the objects just move at random. What if I have videos where one moving object is this limb and this is another moving object? Right? As I move my arm, the motions are not independent. So what happens is, in fact, that this subspace and that subspace, the motion subspaces, because there is a joint, they're not fully independent. So we thought, well, it's going to fail in those cases. And it didn't. And so this is just a sufficient condition. Right. We extended this to the case of this joint. But I'm going to skip it in the spirit of time. And it's a little bit more technical, so I'm just going to skip it. So what do we do with real data? When data are corrupted, we, instead of writing a point exactly as a linear combination of all the others, we penalize the error with some factor mu here. All right? So now your question is very pertinent. With noisy data, it's no longer the case that you're going to get exactly one non-zero coefficient. But as it turns out, my task here is not a perfect reconstruction. My task here is clustering. So as long as I find, at the end of the day, if I connect myself to one neighbor, or two neighbors, or three neighbors, or five, no matter what the dimension of the subspace is, it is OK from the perspective of clustering, as long as they are in the same group that I'm in. And so as you vary this parameter mu, you can get very different solutions for C. Actually, they're not that different, but I'm exaggerating. So the solutions for C could be very different as C changes. But as long as the support of those solutions, then the places where the non-zero coefficients are right, then you still have perfect clustering. All right? I'm going to skip in the spirit of time, but we can have ways of dealing with missing entries. We have ways of dealing with corruptions as well. So to summarize, what is the algorithm really at the end of the day is take every data point, write it as a linear combination of all the other data points, search for a solution that is sparse, and that's going to give you coefficients Cij. That is going to tell you how well point I is expressed by point J. And then construct how similar those 2 points are based on this affinity, Cij plus Cji. And then you just feed this similarity to spectral clustering. Let me skip the low rank stuff as well in the spirit of time. And let me go to the applications. OK, so I've spoken about this from the very beginning. You're given a video, and what you want to do is to segment it into several moving objects. The way we do that is by running a tracking algorithm that will extract a sequence of point trajectories. And now, this is your input data. And what you want to produce as an output is the segmentation. All right? What are the dimensions of these trajectories? Well, every point is two-dimensional, but you measure it for many, many frames. So it's 2 times the number of frames is the dimension of the data. All right? So it's well known in computer vision that if you stack the trajectories into a matrix, so every column here is one of the trajectories, if you only had one object that was moving, this will be a rank 4 factorization. So one moving object induces a 4-dimensional motion subspace, and therefore many objects moving induce many 4-dimensional subspaces. So this is a comparison over 155 videos, none of them of Lena, where we have either 2 moving objects or 3 moving objects. That gives you how many sequences, how many points in average, how many frames they had. And the numbers that are reported here is the error in classification. So how many trajectories were assigned to the wrong group. Okay. So the different rows correspond to different type of scenes. So the first category is there are checkerboard patterns inside the lab so that I can really control that the motion is really generic and independent. So that's the case I expected things to work well. The second row, the traffic, is really I went out in the street and I took videos of cars moving, such as the one that I illustrated before. The interesting thing is that those are a little bit more degenerate because you're not moving in 3 dimensions anymore. You're just moving in a plane, and cars like to go on a straight line typically. So that's why the motions, the rank of the matrices reduces a little bit. And the third case articulated is really people that are moving, and that's where I expected the method to fail and to give the worst answer. That's for the sparse method. For the algebraic method, I expected the opposite. The algebraic method is designed for clustering planes, for example. So the larger the intersection, the better for the method, in fact. And we did observe that. So the algebraic method, which is the first, did very well on low rank and dependent motions, and not as well on the independent ones. And so that's about a 5% error. But the sparse method did relatively equally well in all cases. And we were very surprised to see that it didn't fail in the case of articulated motions. Several years after, we understand why. So Emmanuel Candes at Stanford has looked at this problem and has figured out that the condition of independence is actually not needed, and you can derive weaker conditions under which the method is actually theoretically correct. And so that explains why in all the experiments, whether they are independent or not, it doesn't matter. The algebraic method, I told you that it was not very robust to noise, and as the number of motions increases, it got worse. Here you can see 30% error, which we have been able to reduce to just 2%, 2 to 3%. All right, so overall, a huge improvement. These are some of the videos on temporal segmentation now. So this is Obama during the campaign, frontal view versus side view. So there are 2 video shots, and you can see how the method is able to segment into the 2 video shots. This second example here on the right is a little bit better. So you have, this is the previous campaign. So this is Hillary Clinton. Now you see a lot more motion and zooming in and zooming out. So every subspace is not just a constant image, it's not just rank 1. And the method is automatically able to discover the segmentation into the different video shots. There are many more examples here, fairly more complex. So here you have water, you have a boat, and then you have water again. So that describes the 3 different groups. Here you had a sequence of news with a lot of different type of motions. So you see here there is a person, then there is the ocean, then there is a traffic scene, another traffic scene, and you can get the temporal segmentation by modeling every piece of the video as a low-rank structure. Last example, this is a database of faces. In this particular case, as I said at the very beginning of the talk, if I just vary the illumination conditions and I take lots of pictures of you, you can approximate it very well with a 9-dimensional subspace. So this is a database that has 38 different subjects, and there are 64 images per subject. And what we're showing here is what is the clustering error as a function of how many subjects you take, 2, 4, 6, 10, so on and so forth. Let me just point out to 2 different methods. So this method over here, all right, that is the local subspace affinity method that I talked about earlier that looks at a point and at the k-nearest neighbors. And I also said earlier that if you look at the k-nearest neighbors, at the 10 nearest neighbors for faces, 70% of them are in the wrong group. So that's why you observe that for 10 people, you already have a 60% error. While as you go down, you can get nearly 10% error with the methods based on sparsity. So this way of using sparsity to discover the structure and multi-group structure, it's been really helpful. It can be used for clustering, and it's fairly robust to outliers, which I didn't discuss how we did it, but it is a very minor modification of the method. So to summarize, and sorry that I had to rush to be in time, but we started 15 minutes late. I hope to have convinced you that there is an overwhelming amount of data coming, and that there are many interesting problems that involve clustering and segmentation. We're getting more and more data, and it's getting higher dimensional. And I hope to have convinced you that using unions of subspaces is really a very good model for these high-dimensional data sets that allows you to discover what the structure in the data is, what the different groups are, and that techniques based on sparsity are not only useful for signal reconstruction, that's been traditionally the case, but they can also be expanded to many machine learning applications involving clustering and classification of data. Thank you very much.
Thank you very much, Rene, for this great talk. Very interesting. So, I'm sure we have any questions from the audience. Yes, Michael, please.
Yeah, so my question was about the kind of dimensionality you can handle, because in the examples you showed, either you had like motions of detected targets, or I don't know exactly what you were using with your faces, and because you have this big L1 optimization,
yes.
So can you tell us a little, what are the, typically what's the dimension of the problem you can easily handle?
So we are not at the big data level yet. We started by using standard CVX packages for L1 minimization, which were sort of slow, and we could handle maybe several hundred dimensions and several hundreds, maybe thousands data points. Currently, we have an alternating direction method to solve the problem, and now we can do several thousand dimensions and several thousand data points within a couple of seconds in MATLAB. That's more or less. So you can run, for example, the entire motion segmentation database, which is 155 clustering cases, in about 3 minutes. And that's 155 videos, and includes not only the sparse problem, but also the spectral clustering. So if you want to move to million dimensions and million data points, you will need to do something else. There are people that are working on that right now. So Michal Elad in Israel, I just saw a recent paper of him, where they are developing techniques that are able to scale this up by using stochastic gradient descent type of methods to do optimization, sampling techniques, and things of the like. So the answer is that I cannot tell you there is a technique that is currently working for very high dimensional data sets. This is work of a few months ago. But I'm very confident with all the advances in big data that are coming along, this would be fairly easy to do, because at the end of the day is L1 minimization plus spectral clustering, eigenvector type of problem. So it reduces to fairly standard techniques that people are scaling up a lot these days.
About this question, so when you solve the L1 minimization problem,
yes.
If you have 1,000 variables, for instance, because then you will increase your number of variables squarely, right?
Yes.
Okay, that was it.
Yes.
That's a good answer.
So indeed, if you have n data points, the matrix of coefficients that you're solving for is n squared. It's very sparse, but it's still n squared. But in vision, we're not very scared about that. Like spectral clustering, the type of similarity matrices is number of pixels by number of pixels. So that's not a big number for the kinds of things that we're used to do.
Other questions?
Yes?
What are the limits of the union of subspace model?
The limits of? Speak loud.
Union of subspace model. When do you suppose that data lie in the union of subspace, and when it does not lie in the union?
That's a great question, because if you want to apply this to everything, then you better know that the union of subspaces is a good model for your data. So I don't know if there is a generic answer to this, so let me give you two different ones. One, for the motion segmentation, we can actually model the geometry, model 3D points, rotation, translation, projections. You write it down, you get rank 4. So in that case, it's analytic. So if you are an expert in your specific problem, and you can derive equations of the process for generating the data and show that you get a subspace, that's one route. The other, in the case of phases, is an approximate thing. So you also make modeling assumptions. But at the end of the day, this 9-dimension for phases, it was really more empirical. They took phases, they expanded in terms of spherical harmonics, they looked at the number 9, and they said, well, 90-something% of the energy is already covered. So you can, if you know the groups a priori, if they're labeled, like this chunk corresponds to this group, you can look at the singular value decomposition of the data from each group and see if a subspace is a good model. So my more engineering answer would be, in the same way that you determine whether one subspace is a good model for your data, you can determine whether one subspace is a good model for a subset of your data. But how can you do that when you have no idea about the groups? Then I don't know.
Other questions? It's not the case.
Yeah.
Thank you.